My name is Apoorva Gupta, and I have been in the industry for 3 years now. And besides my introduction and my job in my daily life as a robotics engineer, I get to do a lot of coding, and I use ROS, about which we are going to talk later bit in the slides. And the coolest part I enjoy about coding is that I get to see my code running on a physical hardware or a robot basically, and see robot doing a lot of different tasks. In my free time, I like to read, listen to podcasts, and go on hikes. Today, we are going to discuss autonomous wayfinding, how robots navigate sensor data to map the world. So the purpose of this talk is that I want any coder to kind of be able to gain some insights and be a little bit more knowledgeable and have some knowledge about like if they want to transition to a field of robotics. And I find this field really cool. So we're going to discuss the concept and algorithm for map creation using sensor data from a robot and explain what a map and the sensor data looks like from a coder's point of view. And you will see how your existing coder's knowledge could be applied to robotics. You can connect with me on LinkedIn. I have put my LinkedIn handle in the chat as well. And a little bit about Six River Systems. So Six River Systems is the company I work for, and it was founded by executives at Kiva Robotics back in 2015. We build fulfillment solutions that power the warehouses of the future. So we use software and robotics that improves warehouse efficiency, optimizes labor, and scales quickly and easily. Six River Systems was acquired by Shopify in 2019, and we have been digital by default since then. Another cool thing about my squad at Six River Systems is that we all are female developers in my squad, which I'm very proud of. So, what is the problem that we are trying to solve here? For a robot to perform any real world task, it needs to know what the surroundings look like. The modeling of that environment is what is called mapping. If there is no map, the robot is lost. On this right side, we have different categories. So there's this indoor robot, Chuck, that Six River Systems manufacture, and I work on this robot every day. And this Chuck is in a indoor warehouse. Then we have an undersea robot, we have underground robot, we have a space rover. We have tons of other kind of robots like robotic arms. We have robots from Boston Dynamics, which are humanoids, robotic dogs. We have UAVs or drones as a category of robots as well. But for today's talk, we are going to focus on an indoor robot, something like a Chuck, and what a Chuck would do to map the warehouse, or even something like a robotic vacuum cleaner that's in your house, perhaps, and what it will do to create a map of your house. So let's talk about why creating a map is such a hard problem. First reason is that the sensors are imperfect. So let's say I have a camera, but my camera will have a limited field of view, or it might have some calibration errors in the sensor itself. So in real world, sensors are not perfect. Then the data that we get from sensors is noisy. For example, if I decide that I want to take my camera outdoors and suddenly it starts raining and I want to capture some good images, but my camera lens has water droplets on it and the image that I'm trying to click is all blurry, noisy. So I cannot use that data to create a map, right? Then the environment is constantly changing. What that means is, let's say, today I turn on my vacuum cleaner in my house, which is robotic vacuum cleaner, and it tries to go and clean my living hall. But I decide that today I don't want to keep my couch in that place. I want to move my couch to another new location. And once I have moved my couch, that robotic vacuum cleaner needs to know that I have done that job, and it needs to know the environment has changed. Otherwise, it will go, starts cleaning, and will not clean the block of the floor in which the couch was there previously, and will try to go clean the floor area in which the couch is now. And that is just going to look crazy to the user. And it's not going to do its own job of cleaning the area itself. So robots need to know the environment has changed. The next reason is that there's uncertainty in all the measurements. For example, on this right side, the two rulers are taking the measurement of the same distance but giving us different values. So in all the measurements, there is uncertainty, and we are going to talk about the effects of uncertainty in depth in later slides. So what context do we need if we want to create good maps for a robot? We need coding language, specifically C++ Python, but it's fine if there's any other coding language that you are already aware of. I can tell you the reason of C++ Python in later slides. We need concept of mathematics like probability and coordinate geometry. And my expectation is as an engineers, we all have studied these two concepts at some point in our life. We need a robot. This robot is Chuck that I work on again, but I totally understand that we all don't have access to the robots. We don't have access to the labs, perhaps, which has robots. So the next best thing would be to use ROS. And what is ROS? ROS stands for Robots Operating System. It is an open source set of software libraries and tools that helps you build robotic software. As I mentioned before, we all don't have access to robots, but what if I really want to work on a robot and like see my code on a robot? ROS provides a great simulator called Gazebo, and you can even use a Unity platform. And in that platform, ROS provides a ton of different kind of robots. It has vacuum cleaners, it has robotic arms, it has tons of sensors like LiDAR, wheels, cameras, and you can even model like an indoor space, you can model like an outdoor space, anything you want. So it has great simulation capability and it will provide you a robotic platform to run your code. Then it also has RViz, which is robotic visualization tool. And what that will do is like you can see the data from the sensor in this RViz tool. Then other thing about ROS is that it gets installed in a Linux operating system. And if you don't have a Linux operating system right now, you can use either Parallels or a VirtualBox and install Linux, any Ubuntu machine, and then install ROS in that Ubuntu operating system. The other thing is that I mentioned that we need C++ or Python, and that was because ROS works with these two languages. So you can write your scripts in C++ or Python and make robot perform certain tasks. Like you can write a script that can use your keyboard keys to provide some velocity to the robot. So if I press the front arrow key, then robot can move straight. If I press the left arrow key, robot can turn in the left direction. And I can do like tons of other tasks with ROS. And it also provides an interface for different robotic components to talk to each other. ROS 2 is coming soon, which will be more advanced, which will have more capabilities. And it's just like getting an update for a new language. You can use it, you can start with ROS 1 if you want. And then there is this great wiki.ros.org website, which has tons of tutorials and has a lot of information on how to install ROS and how to like do all the stuff we are going to talk about today. What are we going to talk about today is, first of all, we are going to try to get a robot. Then we are going to understand the data that is provided by the robot. We're going to understand what exactly a map is that robot needs. And then we're going to talk about the SLAM algorithms that we use for creating maps. And SLAM stands for simultaneous localization and mapping. So let's get a robot. The problem that we are trying to solve here is that a robot is in an unknown space and it needs to figure out where it is and what the space looks like. If I apply the same problem on a human, maybe just myself, and see what I'm going to do, right? If When for the first time I landed at Boston Logan International Airport, I was in an unknown environment, like a robot would have been. And at that time, I used my senses, specifically my eye, and my eye was able to look around. It saw this board which said immigration customs and had an arrow around it. My eyes took that image, sent it to my brain. My brain was able to process it, was able to make some sense out of it, and was telling me that, okay, your legs need to do the walking and you need to exit the airport following that arrow direction. And I was able to safely exit out of the airport. Similarly, for a robot to create a good map, it needs three things. First is it needs a method to sense. And for today's talk, we are going to focus on a 2D LiDAR slash laser sensor. Then it needs a brain. Brain could be any CPU, GPU platform. It could be Jetson, NVIDIA's TX2 platform. And then we need wheels, which does the movement, which provides the effect of how robot or how human walks. And with these three components, we can create maps for the robot, and we have our robot ready to go for us. Now on our agenda is understand data provided by robot. So first data that we are going to get is from the sensor, which for us is a 2D LiDAR sensor. What is LiDAR? LiDAR stands for light detection and ranging. It is a remote sensing technology which measures the distance to an object by illuminating the target with laser and then analyzing the reflected light. This is a calculation method which allows you to determine how far the obstacles are from the sensor. In this image on the right side, I have a car, or maybe it could be a robot or anything else, and it has a LiDAR in front of it mounted right there. And we have all these black colored things as, let's say, obstacles or walls in the environment. And the takeaway from this slide is to remember that LiDAR is telling us how far this block is from the car. For example, this block here is, let's say, 5 meters away from the car, but the stop block is 10 meters away from the car. And that is the information that we need to remember. That laser and in ROS, you'll see how data structures is coming in place with ROS. So in ROS, laser data is represented as an array of all these different ranges of like 10 meters, 5 meters, and we are going to use that data later on to create maps. The next data we get is from robots' wheels, which is robots' odometry. Odometry is the use of data from motion sensors like wheel encoders that can estimate the change in position over time relative to a starting location. What does that mean? So for this talk, we are going to say robot's position is in a 2D frame or two-dimensional frame. So it will have a coordinate like X and Y, and then it will have an understanding of theta, which is the heading of the robot. Since the odometry's definition says it's a relative to a starting location, we need some sort of a frame. It could be longitude, latitude frame, but for this talk, we're going to say it's an XY frame. And robot starting location, let's assume to be 0, 0, and theta to be 30 degrees. When robot walks in the straight line, the heading remains the same, so it's pointing in the same direction, but the X and Y has been updated to 10 and 7. So the new location is 10, 7, and 30 degrees. If robot keeps moving straight and then later on at some point it decides that it's bored of looking in the same direction, it wants to change its point of view. So it like tries and takes a turn. And since it's like behind y-axis, it's now at 100 degrees. So what odometry is telling us, how much robot's position has changed with respect to the starting location. So it's going to just give us this 10, 7, theta kind of the data. That's what we are going to get from it. Intuitively, in ROS, odometry will be represented using two things. First, it will be use it will be represented by TF, which is transform frames. Since we have a relative starting location, we need some sort of framing system. And then it will have an odometry message, which would be the actual position and velocity information, which will be the 10 meter, 7 meter, 30 degrees at 2 meters per second of a speed. So we have these two information that we are going to need to create the maps. Let's talk about maps. What is a map? And when we try to imagine it, what do we imagine? In this slide, I have three different categories of map. The first is a world map, second is a Google map, and third is a map of the mall. If I ask what is the thing that's common in all three of them, or what is the information that these maps are providing, we are using maps to navigate safely and reach from one location to the other. Let's say I want to travel by ship and I want to go from Canada to Mexico down here. The only path I can take is from the water. I cannot take path through the land. Depending on my mode of transportation, it could change. Similarly, if I have to take a path from this Google Map location to this question mark location, I can take the highlighted path, but I cannot literally walk from someone's house inside and go straight, right? There are obstacles. And similarly, for a map of the mall, if I have to go to Macy's store, I have to go through this wide feasible path. I cannot go from each of these stores here. I'm going to hit a wall if I try to do that. So the information that a map provides is a landmark, which is the occupied space where a human or anyone cannot go. And then it will provide a feasible space like roads, walking path, countries, or water bodies, which would be a free space where a person can travel through. So we got these two information from all the three maps. What else? So if we think of the format of these maps, how does this map even look like? If I send a screenshot of this map, you will still be able to understand the information in it. So these maps are literally just an image. It could be a JPEG or PNG image, but these images have a ton of information in it. Now, when we want to create a map for a robot, we need to keep in mind that we want robot to be safe, and that map should also help us in navigation. So the three things that's important for a map for a robot is we need information about the space that is occupied, we need information about the space that is free, and we need it to be in a format which is easily readable and understandable by a robot. So let's welcome Occupancy Grid Map. Occupancy Grid Map represents a map of the environment as an evenly spaced field of binary random variables, each representing the presence of an obstacle at that location in the environment. Huge, complicated definition, so we are going to break it down. Since it's a map and maps were images, we are going to say it's a grayscale image, as shown in this bottom corner. Grayscale images are nothing but just black and white images. Then we want this space to be evenly. We don't need to do anything because image has pixels and pixels are already evenly spaced. And this space is represented by a binary random variable, which is nothing but a grid value. And it's represented as a probability. If the probability of the grid cell is 1, that means it's a black color pixel, and black means there is an obstacle. If probability is 0, then it means it's a white color pixel and it's a free space. So if I give this more sense of like a 2D array and I have some grid value of those array, and if I ask a coder that I want to navigate from the start location to this goal location, I am sure at one of the data structure classes in our school, we would have studied any path planning algorithm like A star, binary search tree, or any other like AI search algorithms in graph that you can apply in the same problem which a robot is trying to solve. And you can see how a coder's knowledge can be applied to robotics, and a robot can do successful navigation and autonomous wayfinding. Literally, when a robot is trying to go from start to goal location, it's doing autonomous wayfinding. Very intuitively, occupancy grid is represented as an array in rows. So now let's talk about SLAM. We understood that we have two data that's coming from sensor, LiDAR sensor, and from odometry. We know how the map should look like, but what is this mapping algorithm that's going to create those maps for us? So SLAM is the process by which a robot builds a map of the environment and at the same time uses this map to compute its location. Doesn't it sound like a chicken and egg problem? That we need a map to compute robot's location, but we need pose estimate to build the map. How are we going to solve it? So this gets formulated really nicely in terms of probability. What we can do is we need to find the probability of poses and map given we have observations and movements. Where are these given observation and movements? We kind of talked about it already, which is Z, the observations are nothing but the sensor measurement of how far the obstacles are, and U is nothing but the odometry of the robot. So now in this figure, we're gonna try to figure out what's going on. So we have a robot estimation in yellow triangle. This is the position of the robot, estimated position of the robot. Then we have a landmark, and the estimated position of those landmarks are blue stars. The true location of robot and landmark is non-colored. And in this figure, as I mentioned before, Z is the distance of robot's location from its landmark, or its obstacle, or it's the map point. It's all the same things. So Z is this, and then U is the robot's distance between two robotic positions. So we had these two data. Now in this problem, we are going to apply this probability so that we can create good map. If we apply, if we try to find X and map, which is X is the triangle, M is the star, by applying Z and U, we see that over time, we are able to predict the yellow and the blue locations. So what is the problem here? If you see at the starting location here, the error 1 is really tiny, but over time, this error 2 has increased so much. So we need to understand why this is happening, why there is a huge error that's getting accumulated over time. And then if this keeps happening, we're going to end up with a very bad map that robot will not be able to use. So how we can reduce this huge error that's getting accumulated? We're going to try to figure those questions out. So why there is an error is because there is uncertainty in the measurements, right? We mentioned in the very first slide that one of the problems with mapping, or one of the challenges with mapping, is that every measurement will have uncertainty. So LiDAR measurement will have uncertainty, which is the measurement in Z. The odometry measurement will have uncertainty, which is in the U. And for later slides, we are going to represent uncertainty as an ellipse, like this blue ellipse here. The bigger this ellipse is, the more uncertainty there is in the measurement, and the huge the error would be between the estimated and true locations. So goal of a good algorithm for SLAM would be to reduce the true and estimated position and sensor measurements. So not only reduce the error between the triangles, but we also need to reduce the error between the stars, which is basically the map. So how do we do that? Let's say we have this robot here, and we know the location of this robot because it's at the starting of the frame. Let's assume it's at 0, 0. You will see that it does not have an ellipse around it because we are very sure about the robot's location. But at this location, robot sees a map point M0. And when it sees that point, it has a small ellipse around it because there is uncertainty in the LiDAR sensor measurement. Now, robot moves from its starting location to a new location, and you will see an ellipse around it. Why do we have this ellipse? From the odometry measurement uncertainty, right? So we got this ellipse. Now at this new location, robot tries to see two new map points, M1 and M2. Now they both also have an ellipse around it. And this could just be from the LiDAR sensor measurement as seen in the first slide, but that's not the case. The uncertainty here is because of two reasons. One is the LiDAR uncertainty, which is just a measurement from the sensor. The second is because the odometry measurement itself had uncertainty. What it means is that, let's say, at this location, robot has a 5 centimeter of error, then the location of M1 and M2 will also have 5 centimeter of error. That means this map points M1 and M2 are now correlated with the position of the robot. And this uncertainty is the reason we get into such a huge error at the end of that image before. So now what happens is robot moves again. But now it's moving with respect to M1 and M2, right? So we don't want robot to hit any map points or any obstacles in the map, which is M1 and M2. When robot tries to move in a round path, it is moving with respect to M1 and M2. And you will see at this location, the ellipse is huge, really huge. And why this has happened is that we have now uncertainty in the position, not just because of the odometry, but also because of these M1 and M2 uncertainty. So it's basically increasing over time. Also, the position of the robot is now correlated with map. So what we did was we correlated the map before with the position, and now we correlated the position with the map. Now, if you want to reduce the error, robot needs to see something that it has previously seen in the environment. Something like, because it has seen M0, we're gonna try to make robot see that point again. When this happens, we get a concept called loop closure detection. We got a detection back. So in terms of human, I can say that it basically means, let's say I'm lost in the woods, I start marking the trees, and when I see the first marking again, I can kind of become more certain about my location in the woods. Similarly, when robot does a loop closure detection, it can reduce the uncertainty in its position. Because the position was correlated with the map points M1 and M2, you will see that M1 and M2 also has smaller ellipse as compared to the previous ones. And because the position of this robot was correlated with M1 and M2, this ellipse is also shrunken now. And if you keep doing these loop closure detections over time, you keep reducing the errors in the both position of the robot and all the map points. And this way you can get a really good map for the robot. So let's talk a little bit more about the specific mapping algorithms. The previous one was the overall concept, and now we're going to tie everything together. So we said that we are going to understand the data that was provided by the robot, and that data was the LiDAR scan and the camera data, perhaps. We got limited to LiDAR scan, but we're going to talk a bit more about camera data. And we had odometry. Those two data was sent to the brain of the robot in which mapping algorithm is running. There are 4 algorithms that we're going to talk about, but this is the SLAM algorithms that runs on this LiDAR data and odometry. And what we get as an output is the occupancy map that we saw before. And that's the whole structure of how mapping works on a robot. So what is G-mapping? G-mapping is literally what we saw today. It's literally using the LiDAR scan and odometry and creating grid maps and using probability to do that. I have this wiki page link here, and we're going to post all the links later in the chat during Q&A that people can go to and kind of use this algorithm on a robot in ROS and produce their own occupancy maps. The next algorithm is Google's cartographer. So Google wrote an open source cartographer algorithm that provides a real-time SLAM for 2D and 3D platforms and different sensor configurations. So for this talk, we focused on a 2D LiDAR sensor, but LiDAR could be 3D. There could be other sensors like IMU that can also provide some better data and can be used for creating SLAM algorithm, creating maps using SLAM. That's what Google's cartographer can use as well. So again, a wiki page to the algorithm and a nice paper that people can read later on. Then comes SLAM Toolbox. So again, this is the same laser scan based SLAM algorithm. It can create a 2D map of the space. It has a lot of more like serialization going on, and you can do a lot of different things, like you can reload the map, you can localize on that map, you can merge two different maps, you can even try to manipulate the maps. This GIF on the right side is from an indoor lab in California. And this is a data set used by SLAM Toolbox. This GIF is from that website. And you'll see a tiny robot going around in this indoor space. And if you notice, then you will see that it's going around in circles. So it will go around here, right? So basically, it's going around in circles just so that it can do loop closure detections and correct its map. And the map looks pretty good to me. Also, SLAM Toolbox is default ROS algorithm for ROS2, mapping algorithm for ROS2. RTAB map. So this is a not new, but this is an interesting algorithm, and it's different from all the algorithms we have talked so far. So till now, we were focusing on laser-based mapping algorithms, but RTAB map is a camera-based mapping algorithm. It stands for real-time appearance-based mapping. So it uses an RGBD image, which is red, green, blue depth image, which is nothing but a colored image, which has some sort of understanding of depth as well. And we apply a SLAM approach on that camera data image and do loop closure detections to produce maps. So it's literally the same thing of loop closure detection, SLAM, and producing maps, but just using camera images instead of using LiDAR data. So these are all our mapping algorithms for today's talk. All these resources would be put in the chat box in some time. And another thing I want to mention is that this book, Probabilistic Robotics, is a great resource. It's by Sebastian Thrun. So far today, we just talked about the concepts and the overall algorithm, but all these algorithms requires a lot more probability and a lot more mathematics. And if you want to get into the depth of understanding the maths behind each of the algorithm, this is a great resource. It is a PDF that you can download. It's an ebook. It's free, and try to use it and understand more. And all the rest of the wiki links are on wiki.ros.org. There are tutorials to set up odometry, tutorials to use scan data, and then all the algorithms that we talked about, all four of them also has their own wiki page. You don't need to understand the mathematics to use this algorithm. You can literally download ROS and get a robot in ROS and apply these algorithms on that robot, produce maps. So that's all for today. Thank you for attending my talk and also Connect Reimagine.
Thank you. Thank you for your talk was amazing. Robots are so interesting. I did
Yeah,
leave the resources in the chat for anyone
thank
who
you.
wants to check them out. And if you have any questions, please leave them here in the chat. I did have one question
Yeah,
personally. Is this how robot vacuums work as well?
right, exactly. That's how robot vacuum works.
That's great. That's
They
awesome.
have a LiDAR sensor, a small, like a circular thing perhaps on top of it, and they radiate beams, like light beams, and can figure out how far your legs are or your couch is in the
Yeah.
hall. So, yeah.
That's awesome. Thank you. Okay. Does anyone have any questions? Leave them in the chat, and Apoorva will answer them. Thank you, everyone who joined today's talk.
Yeah, thank you everyone for attending the talk.
There's a question. Do we need a robot kit, or we can use the simulation?
You can use simulation, you don't need anything. And if people are really interested, I can hang out and like you guys can DM me and I can try to send you particular links on how to install ROS. And you don't need anything, you just need your PC. That's it. You don't need a robot. You can use simulation to do everything. You can use ROS to do everything.
That's awesome. And how do the robots account for height and running into things that aren't on the ground?
That's a really good question. So it depends. So there could be robots which have each robots will have different purpose, right? There's not just one single sensor that takes care of navigation. So there is LiDAR sensor, but if you can see the legs of the thing, but if it's hanging, then you will need a camera on top of your robot. So you need to add like more sensors so that it is safe in an environment. So for this question particularly, if things are not on the ground and it's hanging by like some thread on the wall, then a robot will also have camera which will have different field of view so it can see that thing and avoid it.
Awesome.
Thank you, really good question. Also, just to mention this to everyone, we as robotics engineer, we are also kind of work with the whole stack. It's not just ROS and C++ Python. It's a lot more that we do. So any full stack engineers could also transition to robotics. And we, yeah, it's a great field. Any coder can come to robotics, basically.
Awesome. Thank you. And I would like to mention that you can join a few of our next sessions, as well as use the networking feature that Hopin provides, and also check out the expo of all of our sponsors. Thank you, everyone, for joining.